vulture feather mineralization, axial seamount eruption, and a unique meteorite from space. Welcome to the GSOC Geology Hour. I'm Alyssa Smith.
I'm Carrie Gordon.
And I am Benjamin Agyemang.
Hi everybody. So this is my little segment I've been doing every month, which I've been calling Geology in a Nutshell. Our two topics today are going to be a new mineralization process and a bit about the axial seamount. So we're going to start in with mineralization process. So these are the articles where I took these from, and those will be posted in the video description. So our story actually starts back in 1889, very, very shortly, when somebody discovered a 30,000-year-old griffin vulture fossil in the Colli Albani volcanic complex outside of Rome. And so the previous studies have looked at the fossil's external mold, including the head and the neck. But just recently, they started to look at the feather itself. And so what they determined is that feathers are just really rarely preserved anyway. Sometimes they'll be preserved as like a carbonaceous film or like an impression. But this particular feather was replaced by zeolite minerals. And so this is actually the first time that scientists have reported finding soft tissue mineralization by zeolites. So this is a completely different process. So if you're not familiar with zeolites, there seems to be like zeolite fanatics, and I respect that. They're essentially aluminosilicate minerals. So minerals that have aluminum and silica in them, plus a smattering of other stuff. And here's a few examples of just, they're really, really neat. Of course, I took these from MinDat, so they're like museum quality samples, and some of them don't look quite as pretty, but that's just a personal bias, right? So these materials tend to be microporous and microcrystalline, so very, very fine minerals. And these are formed via a process where there's exchange of ions that happens between volcanic glass and saline water. So it's kind of a particular environment for these. Now, zeolites are known to form on biological materials, and that itself isn't new. But usually what happens is these will replace on materials that have silicon and aluminum, but feathers don't have that. So this whole thing has been kind of a complicated puzzle for the scientists. And so what they had said is that there's two kind of ideas, is that, well, I'm going to go into that actually, sorry, this is my next slide. So the hypotheses for this is one of the scientists looking at these underneath a microscope. The idea is that either there's the molecules that are in the decaying material, like those particles will have some sort of affinity for aluminum and silica, and then so you can have a swapping that way. Or it could potentially be related to the pH of the soft tissue as it's decaying. So it's not really quite known what the process is, but it's known that it's new and kind of exciting.
So Blue was wondering, is there potential for the zeolite mineralization process to have happened in other areas and just not been found yet? Or is it hypothesized to be fairly unique to the Colli Albani region?
Wow, that's such a great question. So I pulled up the picture just in case here. My guess is that just thinking statistically, it's probably not the only time it's ever happened. It is probably just the first time we've seen it. But if I'm not mistaken, I think zeolites are pretty fragile on their own, since they're so like little bitty. And I don't know, because this one was kind of trapped in ash. I think from the pictures I was seeing, like the illustrations that they made based on the study, I think that probably the creature was already dead, and then it was buried by a pyroclastic deposit. Couldn't have been too hot, but there had to be, yeah, it's kind of like, how many of these do we actually find versus how many are out there, who's looking for it. So my guess is it's probably not the only time it's happened on Earth, just statistically speaking.
But we just haven't found it. So
Yeah.
my question is, given the fact that a lot of our volcanic material has a lot of zeolites, and some of them are asbestos forming, I know that this isn't one of those situations where, hey, we're going to be out there eating and grinding up this feather because it's kind of unique and rare. But I was just curious if the article that you read, and I should go pull up my own EOS, talked about what of these might be asbestos forming zeolites, or did they even mention that?
Well, I don't know that they did mention. I probably could be incorrect if you look at the article that they cited for this. I looked at it, but I don't remember every detail. And I know that they did scanning electron microscopy on that. And so I'm sure that they identified what the types were.
Yeah.
So that's that. So we're going to go down to the bottom of the ocean now and take a look at the axial seamount. So what is it? This is one I actually have my students in my geology class do like a geology in the news segment for their discussion post a few times a term. And this is one that keeps coming up because it is the most active submarine volcano in the Northeast Pacific Ocean. So you can see it's about 300 miles off the Oregon coast or 500 kilometers. And it's a pretty exciting thing. It's also the first site of, okay, let's try that again. It is the site of the world's first underwater volcano observatory, which is called NEMO, which is, I forgot to write down the, New Millennium Observatory. So it's run through NOAA, the National Oceanic and Atmospheric Agency. So what it is a basaltic hotspot volcano that just happens to coincide with a mid-ocean spreading center. And so in the previous diagram, we had the Juan de Fuca plate and the Pacific plate. So it's sitting on that kind of boundary between the two. And because of its composition and its location, it's just a really unique place to look at volcanic eruptions, hydrothermal vents, and deep sea ecosystems. And the reason why my students have been bringing it up is because it has potential to erupt in 2025. So it's pretty active, and this map here actually shows 3 of the different deposits from ones in 2015, 2011, and 1998. So pretty exciting. And this is being monitored by a program called the Ocean Observatories Initiative. So that's that OOI. And the way they do this is via a regional cable array. So that has electro-optical submarine cables that have high power bandwidth and two-way real-time communication to the seafloor instruments. And so there's at the axial seamount is the one that's circled in red here. That's where they've got, this is in the caldera itself. So there's geophysical instruments, tilt meters, cameras, sensors, things that can do all kinds of analyses, and even it's got different types of spectrometers, so they can be doing chemical analyses, which is just absolutely wild to me. And then there's also the axial base, which is a little bit further out from the caldera itself. And this one is essentially, they've got these things called deep and shallow profiler moorings, which I'm going to show on the next slide. But yeah, this is, there's one that's taking measurements very deep, and there's one that's about 200 meters to just below the surface. So this is a picture of one of those deep profilers. Didn't tell me what all the cool things on it are, but I'm assuming those are the different instruments. And this is one of the ones where they were lowering this down a few years ago, I believe. But the cool thing with this is that these basically act as like an underwater observatory. So there's all kinds of networks with sensors on the seafloor and throughout the ocean water where they're able to get these measurements basically in real time. They said 150 instruments communicating at the speed of light, which is wild. So it's pretty neat. And I guess that's the reason why you do it cabled, so you don't have to worry about transmission through the water. So as far as forecasting goes, so thinking about when this is going to erupt, the ways that they can kind of look into this is through seismicity and then this pattern of inflation and deflation. And those kinds of signals are going to be driven by magma accumulating and also just in the shallow reservoir where this magma is sitting, just increasing pressure. And And this here is what some of the seismic patterns look like for the past 30 days. So one of the things that this article said is that there has been a recent decrease in the number of earthquakes per day. This in itself isn't a huge deal. What it could mean is that instead of the eruption happening this year, it could mean that it happens a few years from now. They said between 2025 and 2030. But it's very likely that it will erupt soon. And so keeping an eye on those different monitoring techniques is going to be important. But this also is not something that will affect us at all. All of the impacts are literally on the ocean floor. So it's not any danger. If I didn't mention it and nobody said anything, you wouldn't even know the difference. But it's pretty cool because most of the volcanoes on Earth are on the ocean floor. So that's it. It was a pretty short one for me today. And yeah, we can chat and
Okay, but
answer questions.
Alyssa, we got a lot of questions.
Oh my
So
goodness.
let me start out with that
Sure.
first one, because I've also got one on that first one. So
Yeah.
moving on to the volcano, are there any other known submarine volcanoes between, say, BC or Southern Alaska and Northern California?
So I pulled this up because I didn't know off the top of my head. But I think there might be some like just volcanoes in general. I mean, and it depends on how, if you're defining like a volcanic edifice, like something that's building a topographic feature that's like a cone. I don't know how many there are, but there's a lot of dots on this map. And I think that the reason why axial volcano is thought to be different is that it may coincide with a hot spot. And so it doesn't, like, I don't know that there's one, I don't know where they are located besides the ones that are ever pointed out to me. But I don't know that there are any like smaller hotspots or anything like at another point on here, but there's definitely volcanoes.
Okay.
Yeah.
And I had to chuckle with the Nemo. That's
Okay.
that's kind of a cool name.
I
Alex
know.
thought that there has been a recent eruption at Axial.
Yeah, I did look at it, and there was one page that I was seeing that was saying that they thought that it might have started, but it was only one, and the rest of the citations I was looking at were like, probably, probably soon. Because the one picture I pulled here, which is the seismic pictures, and this one here, these were both, I took these today.
Mm.
And it didn't say on their monitoring website unless it's in a different spot than everywhere I'm looking.
The report that I heard was that, or read, I can't remember, they discovered it by visual detection. They were actually, they had like, like a regular campaign of going down with submersibles,
Huh.
and they were just going back to a hydrothermal vent community, and it was covered up by lava.
Oh.
So it was a surprise. They didn't know about it until they realized that things had changed in their location. So
Oh, that's
their
wild.
their study site had changed in just, like, I don't know, the last year or something. So apparently there was an eruption that was kind of a stealth eruption.
Thank
Well,
you, Alex.
see, that's how subtle these things can be. You can be looking directly for the information and not find it.
So Gary has a couple questions here. Do we know at what depth this axial volcano is located? And I'm assuming are its eruptions visible from the surface? I think that's hasn't been. And do they ever pose a risk of tsunamis?
So I think to answer a few of those, so I pulled this up because my notes are on this slide. So it's about, the highest part of it is about 1,400 meters below sea level. So pretty far down there. I don't know that the eruptions would be visible from the surface, just knowing what type of eruptions these are. The thing is there's kind of a sweet spot for explosivity with volcanoes between, so if we're thinking of a water magma ratio between like all magma and all water, it's about, I think it's a little less than a 1-to-1 ratio is where you have the most explosive eruptions. If it's less than that, then you've got less water, and it'll be not as explosive. And then if it's more than that, then it'll kind of overwhelm the system and quench it. So a lot of the times with these kind of things, you would get some hydrothermal activity, like black smokers, the vent kind of things that are down there, or you could get pillow basalts and things like that. But basically, there's so much water that the lava that comes out just gets rapidly chilled. So probably not see a lot of that. As far as the earthquakes go, these ones tend to be pretty shallow and they're not very big. Let me pull the one that has this here. So between a magnitude 0 and 2.5, not too big. And then between 0 kilometers depth and 2.5 kilometers. So it's super shallow. And as far as energy goes, even a 2.5 is not that much energy. I mean, it would be if it was really close to us, we'd notice, if in a completely different situation. But as far as that goes, I don't know that it would be, I don't even know if there would even be any displacement. Yeah.
And he's also wondering what publication is EOS? It's the Association for what is it? AGI?
AGU.
AGU.
Yeah.
American Geophysical Union.
There you go.
I should know. I've been a member for how many years? Never made it to any of the meetings. All right. I think we're ready to hear about this crazy meteorite, Ben. What have you been learning? Come share with us.
Right. Thank you very much for the opportunity. And then also the hosts and my supervisor is here, Alex. Thank you for the opportunity, and Melinda, thank you very much for the opportunity. No matter how good you can be, you need to be offered an opportunity. So I'm very grateful for the opportunity that I've been given. Thank you to you all. So today I'll be talking about a unique meteorite from space. It's called Zeolite. So what I want to talk about is the formation process and then also fabrics. Along the line, I'll tell you more about what I mean when I talk about fabrics. So basically, what are meteorites? Somebody may have heard of meteorites. So on Earth, or extraterrestrial rocks that we find here are those that we can call meteorites, or any rock that we can find at a particular location from where it did not form, we can actually call that as a meteorite. So maybe if I should go to maybe Mars, if I should go to Jupiter, if I'm able to, and I find a different rock there, I assess the chemical composition of the rock, and I realize that it is not similar to that of the rock that I can find on Mars or that of what I can find on Jupiter, probably I can call that as a meteorite. So one big question here is that how do we get them? One of the main ways we can get them is gravitational perturbations, where you have gravitational pulls from this planets that we have in space, exerting forces on each other. So from time, it just throws materials into the atmosphere, and then that's how come we get some of these meteorites that we see. And then also we can get them from collision. So in space, we can have collisions going on. And when that happens, you throw materials into the atmosphere. So from the very beginning, you have like a very small body in space, that is the meteorite. And then as it has been thrown from its original position and it is coming down, it is burning in space because of air compression and because of friction. So it is burning. And then eventually it lands on the surface of the Earth, and that's what we probably call the meteorite. So on your far right-hand side, you can see an example of a meteorite. I took this photograph from my supervisor's slide, so courtesy to him. Yeah. So how can we get them? This is just a short summary of how we can get them. So we have this like meteorites traveling from space, and as they travel, they burn, and that is because of the air compression and also as a result of friction. And usually some of them may survive the burning process, some of them may not be able to survive. But usually those that survive the burning process are those that lands on the Earth, and then we see those ones and we pick them as meteorite. And that is how I get my collection of meteorites. Now, somebody may ask, where do these meteorites come from? We have something we call the asteroid belt. So what is the asteroid belt? It has to do with the region of space in between Mars and Jupiter. So if you should go to space, the region it's between Mars and Jupiter, we have a chunk of different rock bodies that are there. And so we call that region the asteroid belt. Now we have different kinds of bodies that we can find in there. So I listed about 4 of those bodies that you can find in there. But these are not the only ones. These are the ones that we know, but there are more to them. If you look at this ring right here, you can see different sized materials or bodies in there. All these ones are bodies that you can find in the asteroid belt. So one of the reasons why we care about them is because they give us important clues. I mean, we have to care about them. We have them, so it is important that we care about this meteorite. One of the reasons is that they give us important clues about the solar system is because they are primitive materials. They are known to have preserved a lot of information from the beginning, from the past. So if you have access to this kind of meteorite, that means that we are having access to other information that existed ancient or several millions of years ago. And we can make geological comparisons. Now there is this particular kind of meteorite we call chondrite. Chondrite is known to have preserved its enrichment. So once we have this kind of meteorite, we can make geological comparisons. We can take rocks from the earth and we can compare it with, and we can see certain kinds of processes that may have happened on earth that caused these rocks to lose their enrichment. And also we can talk about bulk composition. Because we have rocks or some of these meteorites that are unaltered, it means that their minerals are intact, mostly are intact, or even if they have depleted, just a little amount of it. So because these rocks are unaltered, they give us bulk composition, or give us information about the kind of minerals or composition that are in this kind of meteorites. So when these meteorites impact the earth, this is what they form. They form a crater. And so usually when you go to this particular area, the likelihood of you maybe having or seeing meteorites, I mean, now you may not see, but as the event may have happened afresh, if you go there, the likelihood of you seeing maybe a meteorite, there could be a possibility of you finding one. So when they impact the earth, they form this beautiful shape that we call the crater. Okay. Now, there are meteorites, but there are different types of meteorites. They come in different forms, so we can categorize these meteorites. So on the basis of heating and melting and differentiation, we can categorize our meteorites. So we have the iron meteorites, we have the stony meteorites, and then we have stony iron meteorites. Now, these are the 3 major categories of the meteorite. All of these are very, very important, but for the purpose of my research, I am studying Zeolite, which is at the far end. So Zeolite is a type of achondrite, so that is my focus. So if you hear of Zeolite, it's a type of achondrite that has experienced some amount of heating and some amount of melting, but it did not fully melt. So in this case, we said that it has experienced partial melting. It did not fully melt. So these meteorites are differentiated to a certain extent, and they are mainly dominated by olivines and pigeonites. We can have trace amount of trolite and other high pressure phases such as diamond and graphite. Now, on the basis of the minerals that are present, we can categorize them into 2 groups. So we have the olivine pigeonite zeolite, and then we have olivine augite zeolite. Now, olivine pigeonite is all these are minerals. Augite is also a mineral. So on the basis of the kind of mineral that dominates, we can have 2 categories of these zeolite. Now, they are also known to have formed by means of catastrophic disruption of the UPB, where UPB here is a zeolite parent body. Okay, that is what has been proposed for quite some time now. So we know that, okay, zeolite formed by means of catastrophic disruption. But then when I got access to my sample and we're taking a look at them in binoc, we realized that, okay, they have this beautiful texture. They have this beautiful texture, and the texture that we see in there are being formed by the mineral. When I talk about texture, I'm basically talking about the minerals that are there, the shape of the minerals, the arrangement of the minerals, and the relation that exists between this kind of mineral. Now, one striking thing that we noticed about these samples that we observed in the binoculars is that we can see that if you look at the red arrows that are forming there, we can see a black and white band that alternate. So it caught our attention, and then our focus was like, okay, we have to find out what is going on here. So these things you are seeing there are called preferential alignment of mineral grains. These mineral grains have been aligned in a certain orientation. So this alignment is what we are calling fabrics. These alignments are what we are calling fabrics. Now, these fabrics have been associated, or how they form have been linked to crystal settling, which comes from the cumulate origin, and it has also been attributed to flow alignment, which we are going to talk more about that, or possibly maybe plastic deformation. So I'm here to investigate, to tell you which process perhaps led to the formation of these fabrics that we do see. So this meteorite is one of my samples that I'm studying. Now, one big question is, how do these Zeolites form? I'll show you a very beautiful image right after this. So we have accretion, have different materials coming together. And as different materials came together, because you are coming together with different kinds of materials. You have aluminum, radioactive material like aluminum, which is also there. So it increases heating from time to time because aluminum is a radioactive material, and when it decays, it produces heat. So it is part of this accretion process. Now, from time to time, it initiates what we call melting. And from time to time, we have the disruption of the parent body by an impact that happens, followed by cooling. And then later on, we can have a reaccretion process that happens for us to get the Zeolite that we're having. So in this image that I'm showing you, we can see right from the very beginning, we have the accretion process happening, and we have the buildup of the aluminum, which is a radioactive material. Now it gets to a point where the heat that is building up in the accreted material becomes so high, so it causes the materials to segregate. Now this segregation process is what we refer to as differentiation. Now from time to time, this parent body is being impacted by a body. So you cause an explosion happening. So once explosion happens, then you have dispersal of these materials into space. They cool for a certain period of time, and then from time to time, they come together, and then they form a different body, and then they are impacted again, which throws these materials onto the earth, just as I mentioned. So that is how I get my Zeolite. So that is me right there, picking my Zeolite. Now, there has been a strong contention. That relates to the origin of these fabrics. Now, when it comes to the formation of Zeolite, people have proposed that Zeolite perhaps may have formed by a cumulate process, or they have been attributed to a cumulate origin. Others too have attributed the formation of Zeolite to residue origin. Now, in the context of cumulate origin, I'm talking about crystal settling of the mineral grains that forms these kind of fabrics. On the other side, we are talking about residue origin, where it's been initiated by partial melting, so you do not have complete melting. Now, people have proposed that if indeed we are attributing Zeolite to come from origin of cumulate, then perhaps also the fabrics that we do see in Zeolite also may have been formed by a crystal settling process, or also be attributed to cumulate origin. But then that may not necessarily be the case, because the fact that maybe it is coming from the cumulate origin does not necessarily make it a whole that the fabrics that we do see in there are controlled by crystal settling. Okay, so when you have your olivine grains that are settling in a melt, they believe that that process that we call crystal settling is what may have led to the formation of these fabrics. Now, the implication for you to say that these fabrics may have formed by means of crystal settling is that we are supposed to see a lineage. Now, when I talk about fabrics, there are two ways by which I can talk about these fabrics. We can talk about foliations alineations. All these are geological structures. This beautiful image you are seeing here is a simple pole figure. It's just an image that helps us to visualize the kind of geological structures that are inside of these meteorites. So if you tell me that the fabrics in the Eurolites are formed by crystal settling, what you basically mean is that the shortest axis of the olivine is forming a lineation, or the short axis of the olivine aligns such that you are seeing a lineation. Now, this is a foliation for the 100. This is the central part is a lineation. That is how a lineation looks like. If it's just like a clump in the central portion, we call it a lineation. It forms a girdle around the circumference, the inner circumference of this image. We call that a foliation. So if you say these fabrics formed by means of crystal settling, this is the implication for it. So we are supposed to see lineation in the 100, or the shortest axis of the olive must align such that you will form this kind of fabrics. But then, in order for you to be able to choose one of these models and say that, hey, all these meteorite or this Eurolite belongs to this particular origin, there are certain criteria that you must satisfy. You should be able to answer certain questions. So which of these two models are able to answer these questions or are able to explain these features well that I have put in here? We have the observed oxygen isotopic variation, which I'll just mention that subsequently. We have the bulk composition and then the ion depletion that we do see. We also do visualize some reduction rates, and also we do see some shock features. We do see a substantial increase or amount of magnesium numbers in Eurolites that we do have. We also have absence of the basaltic crust. Now, you being able to choose either of these models, you should be able to answer these questions. And one of the aspects that I'm also investigating is that I want to be able to tell the kind of process that form these kind of fabrics, and that is what has been highlighted in red. Okay, so together I should be able to put this together and choose a particular model that supports the kind of fabrics that I'm seeing. So my major goal for this whole research was to, one, determine the fabric forming process, that is one, and then also to characterize the intensity of shock that these Eurolites have experienced. And based on these, I'll be able to infer the petrogenesis or the origin of these Eurolites. Now, what are some of the methods? I have my samples ready. I have my supervisors who are ready and more than willing to help me. Now, the big question is, how am I going to execute this? I make use of the SEM, the scanning electron microscope, which is in the basement of Kramer Hall. So the scanning electron microscope basically has two detectors. We have the EDS and then we have the EBSD. Now, what the EDS does is that it tells me the kind of minerals that are in there. It makes me appreciate visually the kind of minerals that are in there. So I produce beautiful maps. Hey, this is olivine that is in there. This is pigeonite that is in there. This is strolite. And by the way, my samples do have diamond, just that I can't take them out. Very sad. And then also, I make use of the EBSD, the electron basket diffraction. What this does is that it gives me much information about the orientation of this kind of mineral grains. And then I make use of the optical microscope just to study the shock features that are inside of these Eurolite, because at the end of the day, I want to be able to categorize or classify the intensity of shock that these meteorites have experienced. So I make use of the optical microscope. So what did I find? I find quite interesting things that contrast with what people may have suggested about the cumulate origin of Eurolite. Now, this is what we call the pole figure. Okay, it visually shows as the kind of fabrics or geological structures that are present in my Eurolite sample. Now, I'm basically seeing foliations in the 100 and in the 010, which is the shortest axis. But contrary to what may have been proposed, I'm supposed to see lineations in the central image. If you look at the circle in the image, I'm supposed to see a cluster in the central portion instead, other than seeing girdles at the circumference, which is quite surprising. And so I decided to move on to see a different meteorite, or analyze a different meteorite. This is another meteorite. Even though this looks a bit diffuse, you realize that it still mimics, just as mimics what I've shown you previously. So I realized that then what I'm seeing does not necessarily conform to what has been done in the past, even though they are also able to explain certain parts of the fabrics that they are seeing. Now, this is also another meteorite that I classified. I can also see this is the central part, the central circle that I'm seeing here is representing a foliation. Now, this basically tells me that indeed the shortest axis, it tells me that indeed this is the shortest axis of the olivine, and this rather is forming a foliation. So if this is forming a foliation as opposed to what has been proposed in the past, then it is not in agreement to it, because I am not seeing a lineation. I'm not seeing a cluster. I'm not seeing a point maxima here. So it tells me that it is still different from what I'm seeing. So I go on and I keep analyzing, and I'm still seeing similar things. Now, if you look at the far right, I am showing you I'm showing you an image that shows a very hot region at the central part. Now, it just tells me that it represents the long axis of the olivine grain. It represents the long axis of the olivine grain. So I'm still seeing like foliations and lineations in my samples. Okay. And then this is also another sample, but this is just like a very detailed one. This time around, we decided to capture a specific region of our map, and to be able to get like fine details of whatever is happening in there. We perform similar analysis, and then we get same results. Okay. And it goes on and on. We see the same results as well. The very first circle forms a foliation. The second one mimics what I showed you previously. And then this also tells me that, okay, the long axis of the olivine is forming a lineation, right? But this is not necessarily the same if it were to come from a cumulate origin, or if the fabrics actually formed by crystal settling, right? So saying this actually was a little bit, it gives an indication that this is just like a lineation, but then you can see a very diffused indications at the circumference of this inner circle. So I definitely cannot go by the option of saying that this is a lineation, but I mean, this is what I'm still interpreting. So that is what I have for now. So what are the implications for these consistencies that I'm seeing in the fabrics? I'm actually not seeing what they saw in the past, but I'm seeing something different. So what I decided to come up, or what we come up, is that to be able to argue for the cumulate origin by crystal settling, we must see lineations in the O1O, or the shortest axis of the olivine must be able to form lineations, but that is not the case. So per the test results that we have done, we are seeing something different as to what has been proposed in the past. So actually, the presence of these lineations instead of the foliation, instead of the lineations that we are actually seeing, tells us that then there has been some amount of rotation. So the girdles that you are seeing in the inner part, or in the inner circumference of the pole figures, are just telling us that there has been some amount of rotation. And then also in the longest axis part where you are seeing lineation, it tells us that there has been some amount of stretching. Now you ask yourself that which major process can support these kind of indications, or this kind of information that we are getting from our meteorites. So we propose that perhaps this is not really consistent with what had been studied in the past. So then what do? We therefore propose a flow alignment process, which could be a possible candidate. Now, this flow alignment process belongs to the residue origin. In this case, we are talking about a process where we do not have complete melt. We are looking at a system where we do not have so much melt for you to crystallize your minerals to form your fabrics. But in this case, we have some amount of melt, although it's substantial, we do not have so much melt. So this kind of process is what we are describing as the flow alignment process. And amazingly, we are able to explain, if you go for the residue origin, which is characterized by the flow alignment process, we are able to explain these kind of unique features or these aspects that comes with Urolite. We're able to explain them. We see isotopic variations. Ideally, if indeed for accumulate process where you have a system of melt, then we would expect that the isotopic composition of Urolite should be uniform. But in this case, we do see variation. Why? Because we are looking at a system where partial melting existed. So not everything melted. So that means that you have different isotopes in there. So we do see some variations. We also do see bulk composition of bulk composition. We have depletion of iron, especially like incompatible element. That means that there has been some amount of melt extraction. Now, if you have partial melting, that means that you have been able to extract a substantial amount of melt. That is one. Now, we also do have presence of graphite. Now, what I was equally thinking about is that for a cumulate process where you have a system of melt, graphite is less dense. So if you have a system of melt, then I would expect that the graphite will float. But then the cumulate process is unable to account for that. And then we have high magnesium numbers. Now, magnesium would always prefer to be in a solid form, or would prefer to be in a solid state, or prefer to be among maybe rocks that are in their solid state, as opposed to the melt. They prefer to be in a solid system as opposed to the melt. But here we do see higher magnesium numbers. So what does that tell us? It tells us that the parent body that actually disrupted to form the Uralites did not fully melt, as the cumulate model have proposed that there was a system of melt where you are crystallizing your mineral grains to form this kind of fabrics. And then we also do have the absence of basaltic crust. Now, this process is able to tell us, because now we have seen different kinds of Uralites that have feldspaths in them. Now, once you have a basaltic melt being extracted, it means that you are taking all your feldspaths away. So amazingly, this kind of meteorites do not have feldspaths in them. But now we have come across like different kinds of meteorites that do have the feldspaths in them. So at least we know that when these kind of melts were extracted, perhaps the likelihood of you forming other meteorites do exist. And now we are able to explain the fabric's origin by attributing it to the flow alignment process. So in order to justify the flow alignment process, then for instance, if we pour water on the ground and maybe you put a material in there, I would expect that the direction of water flow will go in accordance with whatever you put in the water. If you put a pencil in a flowing water, I would expect the pencil to be in the direction of the flowing water. Now, that is a typical example of a flow alignment process that we are relying on to explain the kinds of fabrics that we see. So in this case, we are saying that, okay, then the shape of the mineral grains or the shape of the olivine grains should conform with the internal atomic structure or the internal atomic orientation of this Uralite. So if you look at this simple image that is right here, the black bands that you are seeing attached to these circles are representing the orientation of the olivine grains. And then the hot regions or the red regions are representing the orientation of the crystal lattice of the minerals, right? So here we can see that there is a consistency between them, or they kind of coincide, or there is an alignment between them. Okay, so in this case, we say the long axis is aligned, and this is same for the second sample that is right there. The orientation of the mineral grains is just in accordance with what we are seeing, or we are trying to describe the orientation of this atomic structure. It has a preferred orientation, so it is just in accordance with the shape of the mineral grains. Now, one thing I didn't mention is why we are just basically hammering on olivine, why I am using olivine and I did not use any other mineral. Now, the reason why I used olivine, or we use olivine, is because it is a major mineral in Erupt. It is the major mineral in olivine, in Erupt. And in terms of its deformation mechanism, or in terms of its deformation process, it is best known. We know it. So based on that, we can study that and tell that, okay, this is how olivine is behaving. And so we're able to tell. So that is the main reason why we decided to go with olivine. And lastly, I also did shock characterization. I used the optical microscope to study the intensity of shock, because once you have an impact disruption, that means that the minerals in the Erupt or in my meteorites have been affected. If you smash your hand into a can drink, an empty can drink, definitely it is going to shrink. It has left an imprint in there. So the same way, just as you are having our Erupt foreign body being disrupted, that means that they hold certain information that tells us that, hey, we have experienced some amount of shock. So I decided to characterize this kind of shock to be able to tell the intensity of shock that these Erupt have experienced. So in my analysis, I looked out for features such as planar fractures. I realized that the blue mineral you are seeing here is fractured. That is an olivine. It's fractured. So I look out for features like this. Now on the upper right here, is what we call mosaicism. Now this I did not see in my Erupt. Now, seeing this tells you that your samples are heavily deformed, or are intensely deformed. I did not see this, so it tells me that, okay, then my samples are not heavily deformed as people may have thought that it is deformed. Okay, so these are some of the features that I was looking out for, counting them and then quantifying them to be able to tell the intensity of shock that these meteorites have experienced. So what did I do? I developed a chart. So on a scale of 1 to 6, I counted the olivine grains and just projected them on a histogram chart. And the particular in time and I count or watch out for the fractures that are within each and olivine grain. So depending on the number of olivine grains that have a particular amount, a particular number of planar fractures in them, I assign them to a particular shock stage. So for one of the samples that I analyzed, I realized that it belongs to shock stage 3. Now, what this means is that it has planar fractures and it has joints. And when you rotate the stage, I do see extinction that happens. When I rotate the stage, the minerals go from its original color to something like black. So that is what it means when you belong to shock stage 3. And then again, I see this one, it tells me that it belongs to shock stage 3. And I also see this, it also belongs to shock stage 3. But then, since I am relying on this and I'm counting them with my eyes, then the likelihood of you exaggerating on what you are seeing could stand. So then, based on one of the models that my supervisor developed, we are now using grains. We are now using olivine grains that have a particular grain size, and we juxtapose it to that of chondrites. And I did that process and I realized that the shock stages that I was getting was way lesser than what they have been assigned to. They are way lesser than what they have been assigned to. If I look at the far right, I see 2.53, I see 2.7. I think the highest that I found in here was 2.72. But then again, if you look at it, when I did it with my naked eye using the optical microscope, I was getting a higher shock feature or a higher shock stage. So that was telling me that, okay, fine, then I may have exaggerated in terms of like assigning the shock stage to it. So this is a very fine and a very beautiful model that was we used in the analysis in terms of being able to tell the intensity of shock that these Erupt have experienced. So in conclusion, this flow alignment process that is attributed to the residue origin best explains the kind of fabrics that we see. And the cumulate model is unable to account for certain unique features that we do see in our Zeolite. And then also if cumulate origin for fabrics formation, if indeed we say that these fabrics formed by crystal settling or are attributed to cumulate origin, then we wouldn't expect to see foliations just as we saw in most of my samples, but instead we would expect to see lineations just as they proposed. However, this is not what I observed in my investigation. So these fabrics could have been formed by crystal settling that is characterized by convective mixing, because these meteorites are associated with the mantle. You know, when you talk about the earth, you're looking at the crust, the mantle, and the core. So we're looking at the mantle where you have a lot of dynamics going on there. So you have flow that is happening there, but you don't have so much magma in there. And it is characterized by a lot of stirring and then mixing, just like how I will stir my soup, but in this case, like at a very, very slower rate. So this brings me to the end of my presentation, and thank you so much for listening. And these are my references.
Well, thank you very much, Ben. I have to admit, when I read the description of what you're going to be talking about, I thought, oh no, I will not understand or gain anything out of this, but I did. And you explained things very well. So thank you very much. And so you can't dig the diamonds out of those pieces of meteorite, huh?
Yeah, I actually saw a very bigger one, but I realized that, hey, I'm using an instrument that magnifies it. So no matter how big it is not significant. I can't do anything with it. So
Okay, so let's back up here to get some of the questions. Early on, Wes was wondering about, was it impacted by the TC3 or was it a TS3? And he just kind of was curious what that TC3 was all about.
So the TC3 is a different body that's have been attributed to the origin of the Zeolite parent body. So in other papers, people have mentioned that it impacted the Zeolite parent body. So that is what people have said in the like in literature. Yeah.
Okay. So, and this is just coming from me. So, can you explain the difference between, because when I think of things flowing, I think of things as being plastic. So what is the difference between what you're talking about with flow as opposed to something that might have deformed through plastic and caused that lineation?
So in the context of my explanation, the flow that I'm talking about is more plastic, not like not like very liquid, but just like how you melt a plastic and it cannot easily move, but you still have materials moving, because by then we didn't have a substantial amount of melt. I wouldn't say it was more than 40%, but the fact that there was some amount of melting there existed. So we're saying that that amount of melt is what helped in moving things around, initiated the process in like moving things around. Yeah. So
Oh,
it is no very, very fluid, but still more plastic. Yeah.
great. Okay, then I did pick that up right. See, I told you were explaining things really well. All right. And Gary had a question. What institutions outside of the US with more stable funding sources are doing significant meteorite research?
So, I'll probably say the National Aeronautics Space Agency. Yeah, NASA. So my supervisor has great affiliations with NASA. So yeah, those are great resources.
All right.
I'll chime in, and I would say that there's a lot of places that do meteorite research around the world. I belong to the Meteorological Society, which is an international organization, and we have people from all around the world that do research. So there's a heavy presence from Europe, as you might expect. NASA and the United States has a lot of research going on. Um, it's everything is under jeopardy now, of course, with the current political situation, but it is a very it's very international.
Well, good.
You
And
can
I
add, you can add Canada,
Yeah.
Chris Hurd's group. You can add Morocco, Hasna's group.
Okay.
There's a lot. There's a big group in Japan, a big group in China. There's even a small group starting in Ghana.
I need to back up here because Gary had an earlier on question. Does the Cascade Meteorite Laboratory have the means to cut through meteorite samples containing bubbles to analyze trapped ancient gas, or does that work have to be sent out to another lab?
My supervisor is here. He'll probably tell you.
We don't do that work at PSU for sure. I mean, yes, we cut samples all the time to make polished sections, but if you want to analyze gas that's inside bubbles, you need a mass spectrometer. You need some way of, getting through the little bit of material that's enclosing the bubble, and then like some sort of laser or something, I would guess, and burning through, and then send that material right into a mass spectrometer to analyze the gas. We don't do that kind of work. That's very specialized work.
I kind of figured that.
Right.
Thank you very much for coming this evening, and I'm glad you could join us and hope to see you again next month.